Okay, so this is going to be problem 71 through 76 of the death packet, problem 71 through 76, beginning with problem 71. 10 students were randomly selected from a high school to take part in a program designed to raise their reading comprehension. Each student took a test before and after, that might be important, they were tested twice, completing the program. It was decided that all students in the school would take part in this program. The mean of the difference between the score after the program and the scores before the program is 16. It was decided that all students in the school would take part in this program during the next school year. Let mu A represent the mean score after the program, and let mu mean score before the program for all students in the school. The 95% confidence interval estimate of the true mean difference for all students is 9 to 23. Which of the following statements is a correct interpretation of the confidence interval? I see the word probability and I really don't even have to do much with it. I just know it's wrong. So what is a confidence interval? This confidence interval, if I'm putting it in context, is we're 95% confident the true population mean difference between before minus after, or after minus before scores lies within the interval 9 to 23. Oh, it lies within the interval. The true mean, that's that true mean, that's the true mean difference, lies within the interval 9 to 23. All right. And basically they're saying this is likely. It's not saying that's going to be the same, but it's likely to be in that interval. Okay. It's likely to be in that interval. There's probably questions on this one, so I'm going to let y'all fill in questions here in just a second. All right, problem number 72. I'm going to couch this one. First off, I believe this came off an AP exam. I do. Every year, there's 5 questions on the AP exam, about 5 questions that are extraordinarily challenging. This would fall into that category. And I mention this not because you can't do it, but I don't want you to stress during the AP exam. You can miss all 5 of those questions and you are going to still and have no idea. Just plain old, don't leave them blank. You should always guess on multiple choice. But even if you missed all of them, you can still do very, very well. Because if you knew the rest of the questions, which you probably don't, but if you did, that would be what? That you got 35 out of 40, which is an 87.5, and you need about a 71 in order to make a 5 on the exam. So don't stress this type of problem. That said, this problem is accessible. I'm actually going to show you the long way to approach this problem because this particular year, there was a shortcut to it, and I will show you the shortcut. This particular year, there's a shortcut, but there have been years since then that the only way you could have approached it is using the long way. So I'm going to start off by showing you the long way because I believe you know how to do that, but it does require some algebra. So based on a large sample, it was found that 10% of the loaves weighed less than 15.34 ounces. So that means if I'm drawing my picture, this area is 0.10 and this is 15.34. It also says, and 20% of the loaves weighed more than 16.3. So this up here is 0.20, this shaded area, and this is 16.31. What are the mean and standard deviation of the distribution of the weights of the loaves of the bread? Well, because they gave you both of these, the shortcut method is just trial and error. But in subsequent years, they would only give you one of these, and then in which case you had to go through this method. So the long method is Z equals X bar minus mu over sigma. So if I plug in what I know, here's what I know for the first one. I know 15.34. I know I'm looking for my mean. I know I don't have my standard deviation, and I also don't have a z-score. However, they do give me an area. And if I do second bars, inverse norm of 0.10, and it's a z-score, so mean is 0, standard deviation of 1, I end up getting negative 1.2815. And I know it needs to be a negative z-score because I'm below the mean. On the other hand, on the other side, we still have the z equals x minus mu, and I'm going to go ahead and plug in for that one. We know we don't know my mean. We know we don't know the standard deviation. We know the x bar is 16.31. Now this one we have to be a little bit careful on because of the way our calculators work. This is 0.20. This is what we're interested in. But remember, our calculators work from left to right. So this area is 1 minus 0.20, which is 0.80. So second bars, inverse norm, 0.80. And I end up getting 0.8416. Now, that makes sense because I'm above the mean, so consequently it should be positive. So if you had done this and done this with 0.20, you would have gotten a negative. You should have said, "Nope, I need to be above the mean," and so just make it a positive. So I'm going to rearrange this doing some algebra, and this gives me negative 1.2815 sigma, because I multiply this, equals 15.34 minus mu. I'm going to do the same thing with this, and now I have 0.8416 sigma equals 16.31 minus mu. All right. Doesn't matter which one I choose, but I need to multiply the signs by -1. So I'm going to multiply this by -1. This becomes positive. This becomes negative. This becomes positive. And then I'm going to combine these together, so this goes away. There is no longer mu. So 1.2815 plus 0.8416, because we're basically doing systems of equations. You're like, Mr. Spencer, you didn't teach us how to do systems of equation. No, I didn't. Your algebra teacher did. And then we have negative 15.34 plus 16.31. And I end up getting 0.97. Divide both sides by 2.1231. And sigma will equal, divided by 2.1231, 0.4568. And I need to choose the one that's closest. The one that's closest is D, and that's my answer. I could have gone back and plugged back in and solved for a mean if I wanted to. Right, so real quickly. Okay, so the question came, you said I said I was going to show you a shortcut. How do you do it? It's not really a shortcut, but if they happen to give you both of these, you can try it out. All right. So hold on just one moment. So it doesn't matter which one you choose. Let's choose the lower bound just because that's probably easier. This is 0.10. This is 15.34. We don't know our mean. We don't know our standard deviation. So here we go. second vars, norm, CDF, negative infinity, up to 15.34, because that's our shaded area. You're like, well, we don't know what to plug in. Well, because it's a multiple choice test and they gave you both answers, you can try all the numbers. So 15.82, standard deviation 0.48, and I get 0.1586. I'm supposed to get 0.10. That's wrong. I go to the next one. Second vars, norm, CDF. Everything stayed the same except my standard deviation is now 0.69. And I get 0.24. I'm supposed to get 10%. That's wrong. Second vars, norm, CDF. Now my mean is 15.87. This is standard deviation of 0.5. Oops. Excuse me, I did that wrong. 15.34. This should be 15.87. And this should be 0.5. And I get 0.144. That's wrong. Second vars, norm, CDF. Change this to 15.93, standard deviation 0.46. And I get 0.0998. That's pretty close to 10%, but we'll go ahead and check the last one just in case. Second vars, norm, CDF. This is 16. This is 0.5 and 0.0934. Obviously 0.0998 is closer, so my answer is D. And I could have checked it on the upper one as well. Okay, so it's not really a shortcut, but I could do it by trial and error. However, I could only do that because they gave me both the mean and the standard deviation as the answer choices. Had they not given me the mean and the standard deviations as answer choices, they just gave me the mean or they just gave me the standard deviation, I couldn't have done that. Or if they'd been really evil, they could have said none of the above, and that also made it very difficult. But since I knew it had to be one of these and they gave me both, I could do it by trial and error with the calculator. All right, problem number 73. The manager of a factory wants to compare the mean number of units assembled per employee in a week for two new assembly techniques. 200 employees from the factory are randomly selected, and each is randomly assigned to one of the two techniques. After teaching 100 employees one technique and 100 employees the other technique, the manager records the number of units each employee assembles in a week. Which of the following is the most appropriate test? Well, first off, we don't know the standard deviation of, we don't know, well, we have two independent groups. So the fact that we have two independent groups lets me know it's probably a 2-sample T. Shouldn't be one sample because one, I don't have the standard deviation of anything. All right, so I don't have the standard deviation of the population. I'm gonna have to use standard deviation of the sample, so that gets rid of the Z. So the other thing is I have two groups. So if I'm doing it twice, if I have something twice, it's going to be one of these two. So if it's one of these two, why isn't it paired? Well, I do have equal sample sizes, so that's possible. But basically I have one group versus another group. No one was tested twice and there was no natural pairing. There's no natural coupling or pairing, and I have one group versus another group, two independent groups, 2 sample. Once again, this is one of the most difficult problems in all of AP Stats right here. This is one of the ones that if it showed, and has been on an AP exam, it's actually shown up more than once on an AP exam. This type of problem is extremely challenging. So I'm going to do the best I can to explain it. But once again, it's not one that'll crush you if you don't understand it, but try. As lab partners, Sally and Betty collected data for a significance test. Both calculated the same Z statistic, but Sally found the results were significant alpha equal 0.05, while Betty found that the results were not. When checking the results, the women found that the only difference in their work was that Sally used a two-sided test and Betty used a one-sided. So let's set this out. Sally, Betty. This is one tail. This is two tail. So this is going to be a not equal, and this is going to be either a less than or greater than. We don't know which. Not significant. And this one said they were significant. So let's start this off. And let me pause for one moment while I check something out on my own. All right, so this case, so alpha in this case is 0.05. Alpha in this case is also 0.05. Well, remember, alpha is the area in the tails. So the area in this tail is 0.025, and the area in this tail is also 0.025. Because it's the sum of the areas. We'll deal with Betty in just a moment. So I want to find what this value could be. So second var's inverse norm, and I know it's an inverse norm because it's a z, is 0.025. So this is negative 1.96. So this value could be negative 1.96, or it could be as high as 1.96. So any direction this way or any direction this way, we would have rejected. So when I look at this, if there's a value greater than 1.96, it turns out there's no value greater than 1.96. So it couldn't be any of the positive values. So I need a value to be this way. And the only value less than negative 1.96 is this. So that is the only way Sally could have rejected. But your question is, well, wait a second, but Betty didn't reject. What if, so she did a one tail lower tail. We don't know if she did, but let's just assume that she did. So let's do this. Second var's inverse norm, 0.05. Well, anything below 1.645 would have rejected. Well, that's below 1.645, so it can't be that. How did she not reject? So that would have been if it was a lower tail. Well, what if she had done an upper tail? Well, if she'd done an upper tail, her rejection zone would be in positive 1.645, and she could have only rejected if she had a value greater than 1.645. So anything less than that, she would not have rejected, while Betty would have rejected. So basically, we know that Sally had to have had a negative 1.96, and she had to have had, or Betty had a negative 1.98, and this one, if she got that same negative 1.98, because she did an upper tail, she would have failed to reject. She would have rejected with a lower tail, but obviously she must have done an upper tail and failed to reject. One of the most confusing problems there is. So the question came up on the Sally and Betty question as to why for Betty, I started off with a less than test, and then I swapped over to a greater than test. That's a really valid question. So first off, we know that if Sally had a negative 1.98, that's going to be in her rejection zone. There was nothing in the upper rejection zone. So I know that she would have rejected with this. And I'm like, well, that's a lower tail. So let's see what happens if I did a lower tail for Betty. Well, with a lower tail for Betty, I get a negative 1.645. And anything less than negative 1.645, she would have rejected. Well, Sally's statistic was negative 1.98. So I brought that over here and I was like, ooh, that's in the rejection zone. So Betty would have rejected, and she's supposed to have not rejected. How could she have not rejected? Well, obviously with a lower tail, she's rejecting. What would have happened if I had the same situation and made it an upper tail? If I made it an upper tail, anything above 1.645, Betty would have rejected. Well, what was this test statistic? Negative 1.98. So had Betty used an upper tail, she would have had to have a 1.645 score, when in fact it was a negative 1.98. So she would not have rejected because this is not in the rejection zone. It's not in this shaded area. So why did I start with this one? I started with a lower tail just because that was a lower tail. Turns out they would have both rejected, so that doesn't give me my answer. So then I was like, well, would she have rejected if it had been an upper tail? And it turns out she wouldn't have. So it had to be Sally did a two tail and it ended up being on the lower side. Betty did a one tail upper tail and she still had that negative 1.98. Because the one thing I know for sure is they had the same test statistic, but this one rejected and this one failed to reject. All right, number 75. I hope you stayed along for this one because this is one of the easiest problems in all of AP statistics, but people forget about it because they forget about this particular function on the calculator, but absolutely one of the easiest. So a test of hypothesis, mean equals 0, alternative greater than 0 was concluded using a sample of size 7. This is going to be important. The test statistic was t equals 1.935, which of the following is closest to the p-value. So immediately we're like, okay, everyone's like, okay, stats, test, t-test, and they go, mean 0. Cool, fine. X bar, 1.935. I don't have a standard deviation. I don't know what to do. And they think, oh my gosh, I don't know this, and they get all scared. And the reason why is because they gave us a t statistic. So we're actually in the wrong part of the calculator. So this is, like I said, it's an easy test question, but you're in the wrong part of the calculator. So let's draw a picture of this. Let's just slow down. We know the t statistic is centered on 0. And we know we have 1.935 is our t value, and we know it's greater than. So let's go to a different part of the calculator. Second vars. TCDF. My lower bound, 1.935. My upper bound is infinity. My degrees of freedom, 7 minus 1, or just 6. And we end up getting 0.0505. Closest answer right there. All right, so question 76, and I'm going to use this moment for a little bit of a teachable moment. The p-value for a two-sided test is 0.10. If the test had been one-sided, what would be the p-value? First off, if you go from one-sided to two-sided, you always double your p-value. So if your p-value had been 0.03 and it was one-sided, you change it, make it a not equal to, you're doubling it, it'll be 0.06. So one-sided to two-sided, you always double. And you're like, okay, always double from one side to two-sided. So that means I'm going to half going from two-sided to one-sided. Hold on, sort of. That's the problem, sort of. So the p-value for a two-sided test is 0.10. So here's my drawing. I have a p-value and it's 0.05 and 0.05 because my area is in my tails for a two-tail. All right. So this is a two-tail. Now I'm going to go to a one-tail. And I don't care whether you choose an upper tail or a lower tail. Let's just say we chose an upper tail. Well, if I did that, you're like, okay, 0.05, that's half. That's what I said. And I'm like, well, yeah, true. But if my test statistic, what if I had drawn it this way? Then what would it have been? It would have been 1 minus 0.05, which is 0.95. So it depends on the direction of the alternative hypothesis. It's either going to be half. So if I go from one tail to two tail, it's either going to be half or 1 minus the half. So one tail to two tail is a doubling. From two tail to one tail is half or 1 minus the half. One tail to two tail is doubling. From two tail to one tail is going to be half or 1 minus the half. Okay. All right, I'm going to add two questions that I did not do last time, which were problems number 25 and 29, because I skipped them last time, and that way those people that were here last time will catch those answers, and then they don't have to stay unless they want to for some reason. So I'm going to look at problems 25 and 29. So a researcher believes that, and the reason I skipped number 25 is it was a two sample, so it was actually in the wrong section. So we didn't know how to do two sample T's at the time. So this is a two sample T. So a researcher believes that a new diet should improve weight gain in laboratory mice. If the average gain for 12 mice on the diet is 5.3 with a standard deviation of 0.5, while control mice on the old diet gain an average of 5 ounces with a standard deviation of 0.4. Where is the p-value? So here's what we need to do. This is going to be a two sample T stat test number 4. And the new diet was 5.3 with a standard deviation of 0.5, and that was 12 mice. The old diet was a standard deviation of 5 with a standard deviation of 0.4. Oops, not 1.4, but 0.4. And a sample size 15. And what were we looking for? Improve weight gain. So the HO would be mu1 equals mu2, where this is the new, this is the old. The alternative, as the way I input in the calculator, because I put alternate, when mu new is greater than mu old, because that was the order I went in. I put the new in first. So in this case, I need a greater than, greater than. We never pool. And I get a p-value of 0.0529. Well, that p-value happens to be between 0.05 and 0.10. So this is going to be letter D. Okay. All right, number 29 is the question I skipped last time, and that's because I got hung up on it because I was looking for a really elegant mathematical solution to it, as opposed to just a plug and chug. And actually, the only way to really do this is with an ugly plug and chug. So this is not going to be beautiful and elegant. There's no way to do it in that way. We're going to have to do an ugly plug and chug. So basically you're like, well, what does that mean? Well, that means I'm going to have to run a confidence interval at 48%, 90%, 95, 96, and 99. And what ultimately the question is, the number of 911 calls per day in a small Midwestern town is noted for a sample of 60 days with X bar is 23.4 and the standard deviation is 3.7. With what degree of confidence can we assert that the mean number of 911 calls per day is between 22.4 and 24.4? So I need to know these need to be within the interval. Okay. So here we go. Stat, test, and I know it's a t interval because it's a standard deviation of the sample. So that means I have to work with a t. Oops, excuse me. Stat, test, t interval, which is number 8. My mean is 23.4. Standard deviation of the sample is 3.7. In a sample of 60. So let's try the confidence level of 0.48. When I do a confidence level of 0.48, is 22.4 and 24.4 in that interval? And the answer, no, they do not fall in that interval. They fall outside, so it can't be done that. If I go to stats, test, a t interval, and I widen it out to 0.90. Once again, 22.4 falls below the interval, 24.4 falls above the interval, so it's not a 90% interval because they're not contained in this. It has to be between that. So then I go stat test a t interval. And this is one that's easy to make a mistake on because we see 22.44 and it's like, well, is 22.4 and is 24.356 in that, or is 24.4 in that interval? And it's not. 24.4 is above that interval. So that doesn't work for that one. So stats test number 8.96 and 24.4 is below this value and 22.4 is above this value. So both values are contained within the interval. So the interval, the narrowest interval that contains both values is 96%. And there's no elegant mathematical way to approach that.